Thank you. Thank you, everybody. Good afternoon. So just for time's sake, I'm going to dive right into the presentation. And when I tried to prepare this presentation, and I promised, OK, I'm going to give 3 examples, not until I started preparing the slides and I found out that was very ambitious, because truly it is the same application of the same method, but to 3 different research projects. So I'm going to jump right into it. So the topic I'm going to talk about today is empirical mode decomposition, Hilbert-Huang transform, and their applications. So I'm going to give a very brief introduction and talk a little bit about time frequency analysis, and then we're going to talk about the basic principles and the concept of the EMD, or empirical mode decomposition, and I'm going to give a few examples. Did anyone feel my voice got that little bit nervousness in it? That's going to be one of the applications I'm going to talk about a little bit later. So the traditional signal analysis methods, including mainly the time domain analysis and the frequency domain analysis. The time domain analysis basically is what we're used to, is look at, OK, there's a signal at a certain time, what is the amplitude? And then you can calculate the associated characteristics, energy, power, so on and so forth. Versus in the frequency domain, the traditional way of analyzing a signal is to basically take a Fourier transform. There you see what frequency contents are there in a signal. However, in a time domain analysis, you completely lose the resolution of frequency. For example, if you're listening to a piece of music, right? So you look at the signal and say, OK, well, this is a signal of a piece of music, but is a C note in there? Is a D note in there? You don't know, because you really don't know what frequency it is. Versus, if you take the Fourier transform and take that into the frequency domain. OK, here you go. You see the C note, you see the D note, you see all these notes. But you do not know when exactly those notes happened in the piece of music. So that's what I meant by time domain analysis loses the frequency resolution and vice versa. So there's some methods that try to address this issue. That is basically to look at the signal magnitude simultaneously in both time and frequency domains. Okay, so some of the predominant methods, including like short time Fourier transform, or known as STFT, and including the Gabor transforms, wavelets, that's another one that has been very popular, and bilinear time frequency distribution, the modified Wigner distribution functions. But all these methods, what they do is they really use the predefined functions, wavelets, for example. Right? You have a model wavelet that can be precisely described by a mathematical formula. And then you use dilation and scaling basically to slide that function through a signal and see how well that actual signal matches with a predefined function. So today I'm going to introduce a new method called empirical mode decomposition. And this method was first invented by a person named Hilbert-Huang. Dr. Huang used to be a professor at NC State University and later worked for NASA for many years. And when he retired, he was a fellow at NASA. So the basic concept of empirical mode decomposition is to identify proper time scales that reveals physical characteristics of a signal. In other words, what you are trying to extract is using this method to extract some functions called IMF, which I'll explain a little bit later, the IMF functions that are intrinsic to the signal itself. And those functions basically are called IMFs, or intrinsic mode functions, which possess satisfying two basic conditions. Number one is in the whole data set, the number of extrema and zero crossings must be equal or differ by at most 1. So now if you picture that in your head, the number of extremas, meaning both either maxima or minima, and the zero crossing points. If the numbers are equal or differ by at most one, meaning it's kind of oscillatory. Okay, so the second one is at any point, the mean value of the envelopes defined by local extrema is 0. Okay, should be 0. So that basically, if you picture that in your head, this function is going to be oscillatory in nature, but amplitude can be changed, and so is the frequency. It's not a singular frequency, and it's not a constant envelope. So all of a sudden, you kind of, in your head, you got this kind of FMAM type of signals going. And those signals are called intrinsic mode functions that represent the basic or physical characteristics of a signal. So, and I probably should, talk a little bit about this EMD process really is an iterative process. Okay, so you basically extract one IMF and then subtract that from the original signal, and go back again, apply the same procedure to extract the next IMF, and so on and so forth. So from that perspective, if you think about it, basically this method acts like a filter, or filter banks. So because basically the first path, it extracts the highest frequency contents, not a frequency content. So the highest frequency content, so basically a small band through the signal, and then the next highest frequency, next highest frequency band, so on and so forth. So this basically describes the general procedure of how this EMD works. And then by some definition, I'll give some definition, when you perform this procedure, there are multiple parameters that you can use as a stopping criteria. Say, okay, this is enough signals extracted from the original signal, stop now. And including all this. But the most important one is what we call the standard deviation, okay, between the two adjacent IMFs you extracted. So that can be expressed as such. I'm just giving the background right now. Ignore the mathematics. It's okay. When we talk about specific applications, things will come together. So just for completeness, a few definitions. Okay, so first of all, the Hilbert-Huang transform. If you look at that, suppose we obtain n IMFs from a signal, then each one can be used to form an analytic function. So if you recall, most of you, I'm sure you do, the analytic function is basically defined as the function itself serving as a real part of that function, of the analytic function. And then the imaginary part of the analytic function is the Hilbert transform of the original signal, which is the original signal convolves with 1 over pi t. Okay? So, and then the original signal can be reconstructed or expressed as the summation of the real part of all the analytic functions. Actually, we went around and around. If you look at that, the essence is, yeah, a signal can be reconstructed as the summation of all the IMFs. So, and then we can define the marginal spectrum as such, as well as instantaneous energy as such. So I'm not going to get into the details of those. Here I'll give you an example of how EMD works. Let's say we manually construct a function as such. So x of t is equals to a summation of sine and cosine functions. So this first plot here is the original data. That is a summation of all these functions. So as you can see, you have 5 different frequencies from 80 hertz all the way down to 3 hertz, and with varying amplitudes. By applying the EMD, empirical mode decomposition method, basically, if you look at that, IMF 1, 2, 3, 4, 5, representing those 5 components respectively. I'm trying to look for something, but that's okay. So if you look at the last one, for example, if you count the peaks, right? So there are 3 peaks, and that's the 3 Hertz signal. Notice the time scale is to 1 second. And if you look at the second one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see 10 peaks. That's your 10 Hertz signal. Also notice, you look at the amplitude too. The cosine, the 10 Hertz signal is about 0.4 on the scale, versus the first one, 80 Hertz signal with a magnitude of 1. So you just get the basic idea of how to extract the signals that are intrinsic to represent the physical characteristics of a signal. And then associated with that, we can plot that by looking at the time frequency domain. If you look at that, this is your time, and this is your frequency, and the color basically represents the magnitude. So you are representing a signal's magnitude in the frequency and time domain simultaneously. So for example, if you look at this blue line here, that blue line is somewhere around here, so okay, that's your 0.3 magnitude. And it also tells you it is at about 3 Hertz, and it lasts all the time of the duration of the signal. Then, of course, the marginal spectrum can be represented like that, and so is the energy spectrum. So the first example I'm going to give you is what we call the voice stress analysis. Okay, some of the voice stress, basically some of the characteristics of voice stress analysis is it's non-intrusive, so no physical connection, so clandestine functions, inexpensive, and it can be applied, especially like a lie detector, priority response. Sometimes, you really, the emergency responders, when they receive a call, first of all, is this a true emergency or not? Which one is more urgent? Through the stress in voice, basically, you make that determination and you make a decision what to do next. How to do that? The VSA basically is a detection of fluctuations of physiological microtremors. So when you think about that, basically when you talk, the muscle moves, and there is a microtremor actually in the vocal cord as well. And that, under normal conditions, that frequency is in the range between 8 to 12 Hertz. But when a person is under stress and speaks that voice with stress, it shifts the frequency and it changes the magnitude of that microtremor. So therefore, by extracting the information of a person's voice, you have an opportunity to actually detect whether or not there's stress in that person's voice. So what we did is, here's an example. We used that data set that is commonly used for voice stress analysis. And this is actually an FFT, fast Fourier transform of the signal voice samples. And if you look at that, the neutral is depicted by the blue, and the medium stress is depicted by magenta or kind of maroon type of color, and the highly stressed signal is depicted by green. So if you look at originally, this blue signal, the microtremor, is right around 10, 12 Hertz or so. And when the person is under stress, those microtremors get shifted. Okay, shifted. I'll give you a little bit more example. So here's what we looked at. Say, okay, the neutral, there's no stress. So if you look at the magnitude and the frequency versus with the medium stress, you see the amplitude change. And so it's the frequency, and so it's for the high stress. Don't have time, I'm watching the time, and so don't have the time to get into all the details, but if you're interested, please feel free to contact me. We'll have the publications I will be happy to share with you. So we basically detected or experimented with 3 sets of data. Okay, so we experimented simulated stress, And basically like this. So we basically use the information from the database, different people with different speaking styles, with different accent. For example, male general US accent, or male Boston US accent, and a New York accent. And so it's all in the database, and that database was first constructed by MIT at Lincoln Lab. And basically, if you look at the results, it's not very clear, but there's one in that neutral, and you see those frequencies did not get shifted from the neutral, or the speaking styles, like I say, softly speaking. I'm not under stress, I'm just speaking a little bit softly, or loudly, or just fast. So you will see the frequencies stay in the same range. However, when you see some angry, or some really moderate stress condition or high stress condition, you'll see the frequencies shooting up. Frequencies shooting up. That means shifting away from where the reference is. And then we tested some actual stressed voice. So actual stressed voice, basically, the researchers or the database builders, they put people or the subjects on a roller coaster. So to simulate that free fall, and so let people scream. And those two roller coasters used were Screaming Machine and Free Fall. Those are the names of the roller coasters. So if you look at that, apparently, in a female sample, the neutral, there's no stress, frequency was at 12.76 hertz. But when it's under stress, especially under the scream condition, put it on a scream machine condition, that voice gets really high frequency, which makes sense, right? So that makes sense. So, and now you look at that for the male sample, it's very similar. Very similar. And we did, some of the deceptive scenarios, and this actually was performed at my previous institution with the help of one of my former graduate students. So basically what we did is we created a scenario and gave those test subjects very specific instructions. So a person comes in, I'll give a paper to him and say, okay, there's a plastic box in one room. Go ahead and take the $50 in the box as well as the cigar and hide it, on you. And then go to the interview room to answer the questions. And then some test subjects as a control group, we instructed them and said, okay, don't do anything. Just go to the room and go to the interview room. So for that matter, we were trying to compare whether or not, so the deceptive subject would, present stress in the voices when they answer the questions. So the interview process, basically we used what we call the modified zone of comparison, or MZOC, and basically is the interleaved questions. So you have, let's just say, a set of 15 to 20 questions. One question is irrelevant. How you doing? And then the second question would be relevant to that. Did you steal that $50? And then next question has nothing to do with the scenario, and so on and so forth. So that's one of the ways of constructing the questions. Question number 10. Question number 10 is right here. Right here. So if you look at that, non-deceptive, subject, it's pretty relaxed. Versus here, you see, the frequency shoots up. And that one is deceptive subject, number 2 was even more obvious. I didn't do it, but yeah, I have it right in my pocket. So that's the first example. And the second example I'm going to give you of the application of EMD and HHT is what we call they did the involuntary hand tremor detection. So, and I think Justin probably does a lot of work in that. I saw some of the pictures that are very similar to what I'm going to show you, but yours is much more sophisticated, I have to say. So this is basically, for example, involuntary hand tremor could be physiological. And let's say, for example, we ask somebody, okay, to stretch your arm and hold a 10-pound, dumbbell, for a minute. And then let me test your muscles so you will feel like it's tremoring. Or it could be pathological. It's a Parkinson's disease. So therefore, you need to detect and see, provide the treatment appropriately. So this was actually a test bed we constructed, doing the research with a graduate student. And basically, we used an arm, and this hand itself was actually from General Dynamics, the ballistics lab. So with that specific material, right, that really simulates true, human hand. And we basically implemented 2 actuators to move the hand and the arm separately or simultaneously. So I'll give you a demonstration to just roughly see how actually that moves. This is like basically the arm control, if you look at that. So, and of course, we've got all the electronic gadgets there to capture all the information. And here is basically simulated hand control. You see, moves this way. Because the inspiration is like actually, if you look at people when they're tremoring, especially Parkinson's disease, they're always tremoring sort of like that. So, and what we're trying to do is detect that magnitude and apply counterforce, and actually we'll call the digital glove for a person to wear to stop it. And this is a combined. So basically creates a complex signal. The motions look very simple, but the combination actually can be very complex. So can be very complex. And here are some information. For example, we use the three-axis, accelerometers to actually detect the motion. Okay, so basically to detect the acceleration, right? So and to translate that into motion. So this is basically the original data we acquired through the accelerometers. And this is basically a 6 Hertz signal applied to use the arm. And here is the Fourier transform of that to show truly at 3 directions, or 3 spots you're monitoring, you do have the 6 Hertz signal and you have their high-ordered harmonics. So now I want you to also look at, this is what we actually did using extracting IMFs. So if you look at that, the capturing time is 5 seconds. Okay, 5 seconds. And yeah, believe me, I'm not going to count each peak for you, but there are 30 peaks in there, so representing a 6 Hertz signal. But the difference is, if you look at that, at each direction, the IMF also tells you what magnitude of that movement is, amplitude. Therefore, you can apply counterforce or treatment appropriately to stop the tremor. And here's basically the Hilbert-Huang spectrum. So if you look at that, basically most of the signals, that's number 5, the first 0 and the number 5 on the y-axis, you see the signal basically concentrates right around 6 Hertz range. Okay, 6 Hertz range. And of course, we collected a few complex drive frequencies, and the results are similar. Okay, are similar. That gives you the combination of the frequencies at each spot with different magnitude. So therefore, you have all the components. Again, for treatment, you can select appropriate means for that treatment. The third example I'm going to give you is actually network traffic anomaly detection. So basically, internet security is one of the pretty hot topics nowadays, especially when you when you have all of a sudden it could take over by the hacker, or just the whole network would be done. And a lot of times the internet traffic monitoring is based on the number of connections to a node. Just like people were saying, okay, you have a server and all of a sudden you have thousands, tens of thousands connections connected to it and requesting service, and then all of a sudden the server would not work. right? And I'm very proud of this work. And based on this work, based on EMD, we came up actually with 3 very novel measurements to parameters to detect the attacks. The test data, we used the standard KDD data. Again, that was MIT lab, collected those data. And for KDD data, we basically, the detection, most of the people, to come up with the internet traffic detection uses this data set. The first method we came up with is called weighted self-similarity based on the first IMF. That was actually based on the Hurst parameter. Hurst parameter, but however, the difference here is we actually use an adaptive way of calculating chunks of Hurst parameters and do the real-time analysis and comparison. So basically, if you look at what we do, is that we calculate the Hurst value, and we build the Hurst value matrix, and then eventually we calculate the weighted self-similarity. These terms were completely defined by ourselves. Okay, doing the research, completely defined by ourselves. And here's a couple examples. For example, this is a normal traffic. We extracted the first IMF, that's a second picture, and we followed the formula to calculate the weighted self-similarity. And if you look at that, this red here is basically a reference or a template. So now, when we real-time extract this, calculated the self-similarity, compared with the template, and said, okay, it's very well within our threshold, we conclude, okay, network is normal, there's no attacks right now. So basically, specific, I probably should mention this, the attacks we are specifically addressing was the DOS, okay, denial of service attacks. So now, here's another example. If you look at the original data, so remember the y-axis represent the number of connections to a node. So normally it's okay, all of a sudden you see a surge of the connections to that certain node, and our detection method basically detected, yes, here are attacks. Okay. And the third one is basically purely attacks. Okay, these are pure attacks. And then last but not the least, and say, okay, now the text is over. The attacks are over. Okay, so I just give you a snapshot of what's going on here. So some of the test results, as you can see, we tested a lot of data. And basically for DOS attacks, we got about 62% accuracy, real time, remember. But we found out it did not work very well for Neptune type of attacks. So if we take that out, it gives you about 78% of accuracy, which is pretty good when you do real time. The second one is what we call the Pearson's distance, okay, based on the marginal spectrum. Remember, we have the EMD, and we take that integral, that's your marginal spectrum, and basically we define the distance, and then we use that as a parameter to detect. Again, some of the results are here. Here's the attack. And the last but not the least is the second method. If you look at that, the detection rate is actually pretty high. It's about 90%. Okay, 90% real-time detection. And again, if you look at the size of windows we're detecting, it's not trivial. So. And the last one is what we call the rate change of energy density level. So that is basically what detected the marginal energy spectrum and look at the correlations. And then we look at the rate change of the correlation. So, and again, these are two parts and concluded there's no, we basically look at the delta of the energy change rate. And here's, attack-free and with attacks. So if you look at that magenta kind of, the line basically shows the slope, and the slope represents how fast the energy level changes. all of a sudden, the green one, you see M2, the rate changing energy spikes, and say, well, okay, here comes the attacks. So for this method, we got about 76% or so detection rate, so which is not too shabby, okay, which is not too shabby. So those are the 3 examples I would like to give you, and I think I controlled my time pretty well. But before I conclude, I really would like to express my thank you to my former graduate students, these 3 students. Very proud of them. This is just a representative sample of my former graduate students. Niaga was originally from Nigeria, so he got accepted by Purdue and decided, well, he needed to go back to his home country and work there for the government. So he did. And Brent received his PhD from Purdue, and last I know is working for Caterpillar in the controls. Makes sense, right? You do the hand tremor control and stuff like that. And Zhang just graduated 2 years ago, and currently she is a PhD student at Georgia Tech, still continuing with the network security type of work. So with that, I conclude my presentation, and I do have about 10 minutes for your questions. Thank you.